Hello and welcome to this video on Wi-Fi. This video is about 802.11ac MU-MIMO and I would like to share with you some interesting aspects of MU-MIMO. At the time I'm recording this video, end of 2015, MU-MIMO is one of the big things in 802.11ac Wave 2 and a lot of people are talking about it and discussing how great it should be. But it's actually a bit of a complex technology that has some drawbacks as well as advantages. So what I'd like to go through with you is look at the way transmission happens so you understand what happens in the background, and then you can decide on how MU-MIMO is going to help increase the efficiency of the cell. The first thing we need to keep in mind is that 802.11 taught us to love multipath. Up to 11n, multipath was the enemy because the signals bouncing in different surfaces and coming at different times and angles on your receiver would create interferences with the pure direct line of sight original signal. But with the processing techniques, development, and the quality of the receivers and transmitters, we became very good at isolating the main signal from multipath to a point where we could actually use the multipath itself in combination with a real line of sight signal and do something with it. And that's what 11n brought by the ability to use these multiple transmissions with spatial multiplexing, the ability to receive the multipath echoes from different antennas with multi-ratio combining, and the ability to repeat the same signal twice on two transmitters to increase the efficiency, the potency of the signal at the receiver standpoint with transmit beamforming. But if you look at a bit deeper on how this works, in fact, as soon as you send more than one stream, you need multipath. Multipath is a requirement to be able to receive more than one stream. And this is something you can verify with a very simple experiment that I did for you. In this experiment, I brought a controller, an access point, and an 802.11ac in that case, but it could have been 802.11n as well, device into a meeting room with nice walls and therefore multipath, and I tried to see how fast I could get. And you see in my controller, I can see that my device is getting MCS9 and two special streams. Beautiful. The result is a speed of 169 megabit per second. Then I took the same system, exactly the same system, same controller, same access point, same client device, same distance from the AP to the client, by the way. But instead of being in a meeting room, I went outside in the middle of nowhere. I still get the same MCS9, but suddenly the number of special streams I get drops to 1 instead of 2. Why is that? Well, because it's outside, so there is no echo, there is no reflection, there is no multipath anymore. And the result is that I cannot sustain two special streams. So why would that be? Well, if you remember the way OFDM works, you may remember that in the transmission, there is what we call the subcarriers, and a 20 megahertz wide transmission uses 64 of those. Some of them are flat, you see them in black, but some of them are what we call the pilots, and you see them in red here. And what those pilots do is that they send a predetermined sequence of traffic. So it's not bearing any real data, it's a sequence that is well known and well shared between the sender and the receiver. And what the receiver is going to do is to read those pilots and know exactly what is supposed to be there. And the receiver is going to compare what it's actually receiving to what it should be receiving. And the difference between what it is receiving and what it should be receiving, well, that's the surrounding noise. So by comparing what should be there to what is there, the receiver can have a good estimation of the noise figure of the sub-frequencies around that pilot. So that is very useful. So when you send more than one special stream, each of the receiving antennas and radio chain is going to receive some signal and is going to look at this signal in detail, especially the pilot part, and is going to know what is supposed to be in first stream pilot, which is different from what is supposed to be in the second stream pilot. And in the receiver system, some processing unit is going to assign one stream to one of the radio chains and the other stream to the other radio chain. So what the radio chain that is supposed to receive stream 1 is going to do is going to look at the signal that is being received, is going to look at what should be in pilot number 1 for stream number 1, and is basically going to consider that everything else, that is to say, in fact, the noise and the signal for stream number 2, all that is going to be noise. So what your receiver for stream number 1 is going to do is compare what should be in the pilot for stream 1 to what is actually being received and cancel what is extra, considering that this is noise and the stream for radio chain 2 is noise for radio chain 1. So it's going to remove that noise figure, and all that is going to be left is the expected stream 1 data. But of course you understand that this only works if radio chain 1 sees something different from radio chain 2. If there is no multipath, no echo, and you get exactly the same signal on both radio chains, if there is no noise, well, what can you remove? Nothing. If you remove the signal from chain 2 on chain 1, you will remove everything because there is no difference between chain 1 and chain 2. So basically, you have a flat signal on both sides. So sending two streams and receiving two streams only works if radio chain 1 sees something different from radio chain 2, so that the processing unit inside the receiving engine can say, you seem to be receiving the pilots from radio chain 1 loud and clearer than the pilots for radio chain 2. So you on the left do chain 1, you on the right do chain 2. But if both sides receive exactly the same signal, there is no comparison to make, and therefore reception of one-on-one stream is just not possible. Okay, so what do we care for MU-MIMO? Well, because the idea behind MU-MIMO is to be able to send one stream to one station and another stream to another station. But this only works, of course, if the second station can remove the signal that was sent for station number 1 and only keep the signal that was sent for station number 2. So this is pretty much the same logic as my multiple streams. You have to be able to isolate one stream from the other because one stream is going to be for you and the other streams are going to be for some other stations. So you need to be able to deduce that noise to only keep the stream that is for you. And when you send with MU-MIMO from the access point, one thing you do not want is that the noise, which is in fact the traffic or the special stream for the other stations, you don't want that noise to be louder than the useful signal for the target station. If what is sent to me has more noise, more things for the others than my own signal, well, if I remove that noise, my signal is 0. And again, I'm not receiving anything because I removed everything. So my signal, my stream, has to be louder than all the other streams so that I can remove that noise figure which the other streams are and only keep my stream and still be able to read something. So there is some complexity here in the transmission mechanism so that the AP can understand what is the channel state at the receiver level for each of the target stations, so the AP can combine its radio chains and transmissions to create that effect where your stream is louder at your local level than anything else. Okay, so how do we make sure of that? Well, let's dig a little bit deeper. In each and every 802.11 frame, there is what we call a physical header, and the physical header contains a few things, among which what we call the training fields. The training fields are signals that are well known again, and that are here to help the receiving station understand what is coming. And if you take a classical OFDM transmission, so in 11A, 11G, 11N, 11AC, typically what you would see is what we call the short training field first. And if you look at a 20 megahertz transmission, with these 64 subcarriers, among which 48 or 52 of them are being used for actively carrying data, what we do is that we take some of these subcarriers and we send a specific signal there. So, we keep some space between the signal on the frequency domain level, and we send a signal on 12 of these 52 useful carriers. And we send basically a sequence, which as you see is an 800 nanosecond symbol that we repeat 4 times. And because we know the sequence, the receiver is able to read that signal, calibrate its receiver to see the tempo at which we're talking. So that's a nice way for the receiver and transmitter to agree on a sort of a common clock. And it's also a nice way for the receiver to calibrate its reception system to know which subcarrier is where, because we know on which of the 12 we're sending the signal. So that's a nice way to say, okay, so that's subcarrier 1, 2, 3, etc. We can set the receiving frequency set pretty accurately here. If this works, the short training symbol is received properly, then we make the signal a bit more complex and we send next what we call the long training field. And the long training field is expanding the transmission to 48 of these tones instead of just 12. And here again, we're going to send a well-known pattern a certain number of times. And because this time we send on the subcarriers, on almost all of them, it's very useful for the receiver to understand how one signal bleeds into the other. In other words, how one subcarrier signal affects the other. So it's a nice way to estimate the cross correlation, as we say, or the impact of one subcarrier to the other. And this is possible because we already know quite well at what rate we send. That's the clock estimation we did before, and also where the subcarriers are. And that's because we had the short training symbol first. Once this long training field is being sent, then we start sending the real thing, the real data in the back. And that's the frame as we describe it in the 802.11. Actually, there are a bit more of the physical header to send, but the main point is that from now on, what we're transmitting actually carries information that we care about. It's not pure physical alignment of receiver and transmitter. It's also about transmitting information. All right, so what do we care? Well, because when you use MU-MIMO, we're going to use those training fields to be able to understand the RF environment at the receiver and sender. And in 802.11ac, the process is to use what we call null data packets, NDP frames, which are frames that do not carry any information really. They just carry this physical header at the beginning and some marking to identify what we're trying to do here. And the AP is going to send those NDP frames out. Each receiving station is going to collect that frame, look at it, and then respond with what we call the VHT compressed beamforming. That is going to tell the access point from all the carriers I received, this is how I heard each of them. So that's going to help the access point have an exact understanding from each receiving station standpoint of the channel, and that is to say what kind of signal can be gotten on what subcarrier in what conditions. And the AP is going to be able to use that information to map how the signal should be sent so that each stream has a differential, different view for each station, and each station can have one strong stream and the others would be not too strong, so they can be deduced and considered as noise. So once the AP has this collection of information for all the stations in its cell to which it's considering using MU-MIMO, it's going to create groups of stations. And those stations will be grouped together based on compatibility. That is to say, the AP is going to say, look at the way those guys see the channel. I can probably find a way to transmit several spatial streams out, and each of them will be getting a clean spatial stream. And some stations will be different groups because the AP will think or calculate, if I send one stream to this guy, it's going to be so loud on that guy that there is no way that that guy will be able to just deduce that first stream and get its own stream from the noise. They are going to basically cancel each other. It's not going to work. So that's how the AP is going to group devices together. It creates this compatibility matrix that can be very large, right? Because if you have a lot of stations in your cell, who is compatible with whom else can be a pretty complex table to build. So the AP builds these groups, and for each group, stations inside the group are numbered. That's 4 stations that could work together. You'll be station 1, you'll be station 2, you'll be station 3 and 4. Then, when the access point is going to use MU-MIMO, it's going to send its series of streams, all together from all its transmitters, and it's going to target a specific group at a time. It's never going to send across 2 groups at the same time because, again, they are not compatible with each other. So it's going to only take compatible stations, and that's the reason why they are in one group. And then the AP is going to send in its frames an indicator that will contain the group ID, so the stations know that they are receiving this sequence of frame because it's for their group, and the other stations will know that because it's not their group, they can ignore that frame. And then the access point is going to identify inside the group ID which stream is going to be for whom. The way it's labeled in 11AC is a bit weird. That's what you see on the left side. So it's going to say, for example, I'm sending for group 1 and I'm sending 201. So what that says is that beforehand, the AP told these stations, you are going to be group 1 people. And then it told each station, in group 1, you are station 1. In group 2, you're station 3, etc. So each station knows what is its group number, and inside the group, what is its index number, what is its station number. And of course, station 0 is the first one. I'm saying 1, but the first number is 0. So when the group receives that identifier in the group ID that says for group 1 and I'm sending 201, what that means is that this is for group 1. The first station listed in the list is the first station in the group. This is the second station, and this is the third station in this case. So what this says is that the first station should get the first 2 streams, stream 0 and stream 1. The second station should get nothing. There is nothing transmitted for that station at this time. Maybe next transmission, but for now, you don't have any traffic for you. And therefore the next station, which is station 2, that is to say the third station in the group, this one being 0, 1, 2, station 2 is going to have one stream. So that allows the receivers to know that the first station is supposed to consider the first two streams in a transmission. And because the pilots tell us what signal should be in which stream, then that first station is going to be able to receive all that flow, look at the pilots expected for stream 1 and stream 2 on two of its radio chains, compare to what is being received, remove everything else that is not stream 1 on one side and stream 2 on the other, and then cleanly receive stream 1 on one radio chain and stream 2 on the other radio chain. So that's how MU-MIMO is going to work. Challenge, of course, of that is the acknowledgement, because if many stations receive at the same time, who is acknowledging? They cannot acknowledge at the same time. There would be a collision. So MU-MIMO forces a system where one station is going to send a real acknowledgement and the other are going to be using an implicit block ACK, that is to say, we'll send a block ACK later at some point. And also on the grouping side, the matrix can be fairly complex, and the protocol allows for the creation of up to 62 useful groups of stations, but each group cannot have more than 4 users. So if you use 802.11ac MU-MIMO, there is never more than 4 devices in each individual group. So you cannot send to more than 4 stations at a time, basically. Then you can have many groups, but each transmission is only for 4 stations max. So when we'll have 8 special stream access points, there will probably be some fun combinations we'll be able to do here. But if you look at what we have mostly today, which are 4 special streams access points, you understand that the chances that if you send one stream from each of your radio chains, and that stream is going to be exactly the right match for 4 stations, no need to compensate anything, that is very unlikely. The chances that you will have 4 stations that will be somewhere in space in such a position that if you just send a stream out of each of your radio chains, it's going to fall perfectly for those stations, are going to get the first one, stream 1 perfectly, the second one, stream 2 perfectly, the third one, stream 3, etc., without having any issue removing the noise from the others. That is, possible, but such a coincidence that it's very unlikely. So in theory, it's possible, but most serious vendors will not try to claim that because it's so unlikely that it's unrealistic. Most of them are going to tell you, well, we have 4 special streams, and therefore probably at least one of those is going to be used to somewhat compensate, the noise, the multipath, and the environment limitations. And therefore probably the best we'll be able to do is to send to 3 different stations, and the 4th stream is going to be here to create some noise patterns that are going to cross-compensate from one to the other so that each of those 3 stations can actually get a sort of clear signal. So most systems with 4 streams are going to in fact be able to communicate to 3 stations at a time. Of course it can be less, right? You can communicate to 2 stations or 1 station. That's piece of cake, because for each of them, you have 1 extra or even more extra streams that you can use to create this noise pattern cancellation that you need for the proper reception. The frame itself that is being sent to the MU-MIMO users, it'll be strange because it's going to contain a large section that is common to all users so that everybody can understand there is a frame coming. So you have this long trailing field that is going to be common for everybody. So that's everybody understanding that something is coming. But then if you're sending a signal to each different user, you also need each different user to be able to estimate the channel and estimate its own special stream and isolate it from the others. So the result is that your frame, and here I'm talking about 20 MHz, 40 MHz, 80 MHz transmission, the bandwidth itself doesn't matter. Your frame is going to have one large common training field that is simple enough for everybody to be able to understand, those sub-carrier channels, blah, 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 clocking, all the thing we saw together before. But then after this common training field for the entire frame, there will be a tinier training field specific for stream 1, specific for stream 2, etc. And that is going to be used for each of the stations that will have learned from this VHJ SIG here which group is supposed to be receiving that frame and which station has which stream in the group. From there, the stations will know that. So then they will be using that information to know which of those substreams they will need to be able to read properly. And therefore, they will need to have a second training field specific for stream 1, for stream 2, etc. so they can differentiate the useful signal that is for them from the non-useful signal that is for the other guys. So you see that the frame is a bit special. And what is a bit complex with 11AC is that this training signal, we call the sounding system, is very useful for both sides, right? Not only for the sender to know how to send a signal, but also for the receiver to know receiving the signal, how to separate what is useful from the garbage, what is for the others. And if you look at the 11AC Wave 1 or 11N or the previous technologies where there is only SU-MIMO, single user MIMO, if you don't make it right, if sounding doesn't work, well, the worst that can happen is that you cannot read one of the streams and voila, you go back to my outside situation when there is only one stream and that's it. No big deal. But with MU-MIMO, it's more complicated because you have different receivers. So if your calibration, if your sounding doesn't work, if your training doesn't work well, it's not only that you reduce the number of streams, but you create some collisions between the traffic for all the different stations. So in other words, traffic that you intended for station A is going to be garbaged with the traffic intended for station B or C. So it's not only about reducing the efficiency, is that you can damage the entire transmission altogether. Nobody's receiving anything. So that's a big concern. A consequence of that is that we have to do this training often, and it's mandatory. Without it, there is no MU-MIMO. And often means that what you could do every 100 milliseconds or so in previous technologies where devices were expected to move but not so much and not so fast has to be done much more often with MU-MIMO because devices can move at any time and there are many of them and each device's move may be impacting the signal to the others and from the others as well. So you have to recalibrate your channel all the time to make sure that you have a clear and current view of the current state of the channel. And that means that the projections today for MU-MIMO mean that you'll probably have to do this sounding every 10 to 20, 25 milliseconds. And that is very, very often. Every 10 to 25 milliseconds, you have to use these sounding frames to be able to estimate the channel before actually sending traffic. So you'll be wasting time and frames estimating the channels so that you can send to more than one station at a time. And again, it all relies on the fact that the stations are going to have a different view of the channel, right? Because if they see exactly the same signal, they cannot isolate one from the other, and basically all of them receive nothing because they remove everything. So if stations are too close to each other, from the RF standpoint, they have the same type of view of the channel, then it doesn't work either. So that's the complexity of MU-MIMO because stations have to be compatible in their RF view of the channel, but at the same time it has to be different because if it's the same, they are too close, then it doesn't work either. And to spice up things even more, keep in mind that the early part of the frame, the LC, the long trailing symbol, is going to be the one carrying information about the length of the frame. Why does that matter? Because the length of the frame is going to determine the duration of the transmission. If you transmit 1500 bytes with MCS 5, it's not going to send the same time as if you transmit the same amount of byte using MCS 8 or 9. Because with MCS 8 or 9, you have a much higher density of information per wave, and therefore it takes less time to transmit the same amount of data. So what if you have to send 2 frames which are typically going to be of the same size because that's the way Ethernet works on sending frames to the access points. So what if you have to send 2 frames to 2 stations? If you use a very different modulation for each of these 2, one station will be finishing receiving its data part of the frame long before the other one does. And the result is that, well, there is signal that is to whom? Nobody. So what you will have to do for the stations to still be able to evaluate the noise of the channel, and for the station that is still receiving to be able to deduce the right thing from what is received, you'll have to continue sending traffic that is not used by the second station, but is used by the first one to be able to still evaluate the channel noise just like it was on the first part of the frame. So this means that you either have to use the same modulation for both stations, so which means that potentially you're using a modulation that is not very efficient for one of the 2 stations. You could have done better, but because you want to be compatible with the other, you have to go back to a slower modulation so that the transmission takes the same time. Or you use different modulations, but then you use padding on some of the transmission so that the duration of the transmission stays the same. In both cases, you're spending more time sending traffic to a station that you would if you were not using MU-MIMO and were just sending to that one station. So you send to 2, but the result is that one of them may be suboptimally receiving traffic from a performance standpoint. So the consequence is that MU-MIMO is a great way to send traffic to more than one station at a time. And if you have stations that have only one spatial stream capability, being able to send to 4 of these stations at the same time is definitely an advantage over sending to one and then after send to the other. you can send at the same time, so it's a gain. But at the same time, the complexity of MU-MIMO makes that you have to be able to evaluate the channel very often to be able to stay efficient. And also that you have to work on your modulation so that you have a compatibility of the signals between the different stations. And that makes that the signal itself is going to be less efficient on some of the stations. So there are some advantages, there are some drawbacks, and it will all be about the quality of the implementation so that the vendor of the access point can weigh these advantages and drawbacks to determine in what cases it's more advantageous to use MU-MIMO to send to more than one station at a time, and in what other cases, and there may be plenty of those, where it's actually not more efficient after all to use MU-MIMO, and it would be more efficient to speak faster using SU-MIMO to one station at a time and waste less time evaluating the channel. And that means that you may not see MU-MIMO used everywhere. It will be useful somewhere, but not everywhere. I hope this was useful for you, and I would like to thank you for watching.